Hello again, everybody. Welcome back to another screencast lecture. Today we're going to talk about thermal energy and temperature with an emphasis on temperature. This is part 2 of the series. Let's get started. Before we do anything, let's go ahead and review a few key terms that will be helpful for us to know. First of all, energy is defined as the ability to do work, or another way to think about it would be the ability to cause a change. Energy is the ability to cause a change. Two main grouping of energy that we learned about, that would be, that's right, kinetic and potential energy. Kinetic energy is the energy of motion, and of course, that is increased by increasing the speed and or increasing the mass. And potential energy is stored energy. And if we're talking about gravitational potential energy, we are talking about how high the object is in addition to how massive the object is. Both of those things will affect gravitational potential energy. The faster particles in matter are moving, the blank their kinetic energy. Well, again, kinetic energy is based on mass and speed, so the faster the particles are moving, the greater the kinetic energy. Out of these three diagrams, which diagram shows particles at highest kinetic energy? So what you want to look for is you want to look to see where we have the particles with the most mass and the most speed. Well, all of the particles in these diagrams have about the same amount of mass. They're all about the same amount of particles. So speed is going to make the big difference. And if we take a look at this, you can see the bottom left over here. That is going to be representing the highest speed as we see these fast ones kind of zipping across. Bottom left is our winner. Thermal energy. You may recall the definition of thermal energy. Thermal energy is defined as the total energy of all of the particles in the sample. Which diagram shows particles with the greatest thermal energy? Again, we want to look in this case with the amount of particles and how fast they're moving. Well, in this case, it's still going to be the bottom left. It's the same one because they have about the same number of particles and they are moving farthest and fastest on average. The most kinetic energy and the most thermal energy in this bottom left-hand sample. An important concept regarding thermal energy. Number one, more particles equals more thermal energy. So on the left and on the right, these are all moving at the same rate of speed, but there are quite a bit more particles on the left than there are on the right. Therefore, there are more particles in the sample on the left. The other variable would be particle speed. More particle speed equals more thermal energy. If I heat up this end of the metal rod, these particles over here are going to start moving faster. As they move faster, they will spread out more. The metal rod will actually expand, and you will see that the thermal energy is increasing. It's increasing not because of more particles, it's increasing because of more particle speed. Here's a clip. I have here is I have a ball and a ring. Notice they don't fit together. Alright, I can't fit them together. This one does. Woo! Okay, so that one goes through. Any questions? Alright, so what I'm going to do is I'm going to hold this ring in the flame.
Then it makes it bigger, doesn't it?
Well, let's find out. Hopefully. If it doesn't, then my demonstration is kaput. Alright, so I'm just going to hold this in there. Clearly this is probably getting hot. I'm not going to touch it. Unless I want an O brand on my skin. Ow! 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 Yes, that was hot. Ooh, this got burned? Oh, ow, that hurts.
And you said you weren't going to touch it.
I wasn't planning on touching it. Wow, you guys got a special bonus treat today.
I didn't even see it. I turned around.
You didn't see it, but hopefully it's on camera. Ow. Okay, well, the important thing is that it actually did work. Okay, so that's exciting. So now it's kind of stuck on there. So what would I need to do to get it unstuck? I need to heat it up again, which I'm not going to do because my finger is in pain. All right, so we'll hold off on fixing that until a later time. Ow. Okay, thanks. That was fun. So that brings us to this question. The ice fort versus the lit match. Which has more thermal energy? Well, the snow fort has more total thermal energy. That might be a little surprising to some, but why does the snow fort have more total thermal energy? Well, it's a matter of the number of particles. The fort over here has tons more matter, way more particles than the lit match does. So even though the lit match, the particles are moving faster, there's way more total particles in the ice fort, which will be more than enough to have the greater thermal energy. Remember, thermal energy is two parts. It's the number of particles and the speed of the particles. I can increase thermal energy by doing one of two things. I can increase the number of particles and or increasing the amount of energy or speed in each particle. The snow fort has many, many, many more particles than the lit match. Now, finally, for some new stuff. Let's get going. Now, let's talk about temperature. Which has the higher temperature? Let's think about that. Shouldn't be a trick, really. The match has the higher temperature, clearly, much higher temperature. So what is temperature? Let's talk about how temperature is defined. Our definition is based on a couple things. So here we go. Let's take a look at this drawing. Now, do all of the particles in this sample, are they all moving at the same speed? No. Well, this one's moving relatively slowly versus this one here. Look how fast that one's going. So they're not all moving the same speed. Some are definitely moving faster than others. So here's our definition. Temperature is the average, underline the word average kinetic energy of all particles in a substance. It's the average kinetic energy of all particles in a substance. That's a key word. So when you see the word average, that might automatically kind of tune you in that we're probably talking about temperature. Do all of the particles in this block have the same amount of kinetic energy? So let's say this is a metal block. If we start heating up this bottom corner, this particle will have more thermal energy than this particle, more thermal energy than this particle, more thermal energy than this particle. They all have the same amount of mass, yet this one is going to be moving faster than those three. So this part is moving faster, vibrating faster than the others. So no, the kinetic energy is not the same throughout every particle. So no, the bottom left one is vibrating faster than the other particles. Therefore, all of the particles in the block do not have the same kinetic energy. Here's a clip showing particles in motion in a liquid. This is pretty neat. That was a pretty cool little video there. Here is another important point about temperature. Temperature and thermal energy are related, but they are not the same. So there is a connection between the two, but they are not the same thing and should not be used interchangeably. It's easy to do that, but we'll try not to do that. So here's a way to think about this. Imagine if you have an empty tray, and then I put a cup of hot coffee on top of this empty tray. Well, this hot cup of coffee is at 100 degrees Celsius for temperature. That's boiling. A cup of coffee has about 75 kilojoules of thermal energy. So that's the amount of motion and the amount of particles that are in the coffee. That's just a measurement of thermal energy. So let's just say 75 kilojoules. If I double the amount of coffee, so I'd add another cup of coffee and put it on the tray, will I double the temperature? Is the temperature going to be 200 degrees Celsius now? Well, no. The temperature in both mugs is still going to be an average of 100 degrees Celsius. It's not going to get any hotter just because I add another cup of coffee there on the tray. However, the amount of thermal energy, will that double? Yes, in this case, thermal energy is going to double because thermal energy is the motion, so the motion is still moving fast, but we're also counting the amount of particles. Now we have double the amount of particles, so we're going to get double the thermal energy as long as both of them have the same speed of particles. And in this case, yeah, because they both have an average of 100 degrees Celsius temperature. Here's another way to think about it. Let's say we have a piggy bank. Let's say there's $10 in our piggy bank. How much total money do you have? Not a trick question. You don't have to be a math genius to figure this one out. Well, it's $10. There's $10 of total money. That would be like thermal energy, as thermal energy is the total kinetic energy in an object. So let's say this piggy bank has a total of $10 of money in this object. So if I have this piggy bank, it has $10 in it. I have one piggy bank. What is my average money per piggy bank? Again, not a trick question. It's going to be $10, the total amount of money, divided by the total number of piggy banks. So I have $10. I'm going to divide that by one piggy bank. I get $10 per piggy bank. So my average is $10 per piggy bank. That would be like the temperature, as the temperature is the average kinetic energy, not the total kinetic energy. It's the average kinetic energy in an object. Remember what I said. If you hear the word average, that's kind of a trigger in your mind to be thinking temperature versus thermal energy. Thermal energy is total. Average is pointed towards temperature. Now, let's imagine your brother has another piggy bank. It also has $10 in it, and he gives it to you for your birthday. Isn't that fantastic? How much total money do you have now? Well, you had first piggy bank has $10. The second piggy bank also has $10. So now we have $20. Cha-ching. All right, $20 in two banks. Okay, $10 is $20. So $20 in two banks would be the total. So that would be like the total thermal energy, as thermal energy is the total kinetic energy in an object. So particles and speed is total. And now we have two piggy banks with $20 total. What is the average dollars per piggy bank? Well, we do the same thing as we did before. We have $20 now. It's the total amount of money. We're going to divide by the total number of piggy banks, which is 2. So 20 divided by 2 comes out to be $10 per piggy bank. So that $10 per piggy bank, do you think that's more like temperature, or is that more like thermal energy? Well, think about that for a second, and you should think that, yes, again, it's average, so that's going to be more like temperature. $10 average dollars per bank.
Which has
would
more
be like
thermal energy,
temperature,
an iceberg or a cup of hot coffee?
Kinetic energy,
What would your answer
not
be?
the total kinetic
In many
energy
cases,
an
the
object.
first answer
Total
that comes to
kinetic
mind
energy,
when
again,
asked this
that would be the
question is
thermal
that the cup
energy.
of coffee is
Temperature and
obviously
thermal
going to
energy
have
are
more
related,
thermal energy
but
than a
they are
massive
not the
iceberg.
same.
Are we
Here's
talking
Clip.
about thermal energy or temperature? How do we define thermal energy versus temperature? Let's find out. In the English language, the common terms thermal energy, heat, and temperature are often used interchangeably. Although they are closely related terms, they each have different meanings and are measured in different units. What are those differences? Thermal energy is the total amount of kinetic energy of the molecules in a system or an area. Being the total amount of energy in the system or area, thermal energy is impacted by size and mass. The base unit for thermal energy is the joule. Temperature, on the other hand, is measured in degrees Fahrenheit or degrees Celsius. Temperature is the average kinetic energy of a substance or a system. Since it is the average kinetic energy, it is not impacted by size and mass. Does this info change your answer? Let's look at the subtle differences between thermal energy and temperature. Let's start by comparing 1 cup of coffee to 2 cups of coffee. What doubled, temperature or thermal energy? Remember, temperature measures the average kinetic energy. 2 cups of coffee will not have double the temperature of 1 cup of coffee. But 2 cups will have double the thermal energy than 1 cup because the mass or size has doubled. Now what about the 1 cup of coffee versus the iceberg? Remember that all substances above absolute zero, that is 0 degrees Kelvin, have molecular energy. Let's assume the iceberg in this example is at the freezing point of water, 0 degrees Celsius, which equals approximately 270 degrees Kelvin, or 270 degrees above absolute zero. The coffee is likely to be in and around 75 degrees Celsius, which is 350 degrees Kelvin. While there may not be a huge temperature difference between the two in direct comparison of temperature, the iceberg is several thousand times larger than the cup of coffee. Even though the iceberg is at a lower temperature than the coffee, it contains more thermal energy because it is not at absolute zero, and its mass is much greater than the cup of coffee. Therefore, the answer to the question, which has more thermal energy, an iceberg or a cup of hot coffee, is the iceberg, due to its mass.
All right, that was a nice little clip there. Now let's get back to temperature. So how do we measure temperature? We use the tool that is called yep, you know it, of course. It's called a thermometer. The thermometer is the tool for measuring temperature. Here is an example of a type of thermometer. There are more than one type of thermometer. And we call this a Galileo's thermometer. It's pretty cool. The different balls here, they'll either float or sink, determined by the temperature in the room. And the temperature of the room will change the density of the liquid inside the balls, and they'll either go up or down. And I guess my dogs are barking because someone's at the door. Hold on a second. Let's pause here for a minute and take a look at a real Galileo's thermometer. Stand by.
Have what is called the Galileo thermometer. It wasn't invented by Galileo, but the principles that it works on were discovered by him. So how does it work? As you can see, we have the glass on the outside with a fluid on the inside. This fluid is normally water mixed with ethanol. And inside we have these small little balls, each one with a different colored liquid in it. We have some here which are from our old one, which broke. You should be careful with these. They're very delicate and they can break. So if you look carefully at the ball, you can see that it's made of glass and there's a colored fluid inside. And right at the bottom there's a tag with a temperature. And the way this works is that each of these little balls has a different density. And the densities are calibrated by how much fluid is put in and the mass of the tag at the bottom. Because density depends on the volume and on the mass. Each of these little balls has a density that's very close to the density of this fluid. And the density of this fluid changes with temperature. I have some hot water here. Not too hot though. Again, we don't want to break this. So as I put this in the hot water, it starts heating up the fluid on the inside. As this fluid heats up, it expands and its density decreases. Now, the reason this tag here is floating is because its density matches or is equal to the density of this fluid. But as the fluid density decreases, then this will start to sink. You can see here it says 26 degrees. So that was the temperature of the outside. But as it starts to sink, we can see the temperature on the inside starting to increase to 28 degrees. And if we increased the temperature of the fluid even more, then its density would even decrease even more, and then it would start to go below the density of this ball, and then that ball would start to sink. So that's how a Galilean thermometer works.
Okay, we're back. That was the Galileo's thermometer, pretty nifty, and they are available even at Walmart. That's where I got this one. Now let's remember, temperature is a measure of the average amount of motion in molecules. Now I've said that probably now 30 times, so try to remember that. Temperature is based on an average, and for example, if we're talking about air temperature, a high temperature the air molecules are moving fast, and with low temperature air, the molecules are moving relatively slowly. So here you see the higher speed molecules here, they're going to be moving faster and spread out a little bit more. The slower molecules in the colder or cooler air are going to be moving relatively slower, and they're going to be closer together. Bulb thermometers. Bulb thermometers are probably the most common. They are the ones you think about with this red liquid. A bulb thermometer, you can see this area down here, that's called the bulb, and it's filled with this liquid. That liquid could be different things. Mercury was a liquid metal. That was kind of the traditional, original liquid that was used in thermometers. Nowadays, the red liquid is usually alcohol, and that's chosen instead of mercury because it's safer. If the thermometer bulb breaks, it's just alcohol on the floor versus mercury, which is a toxic metal that is an environmental problem. So we don't really use mercury thermometers anymore. Mercury thermometers, though, were pretty neat because they're that shiny silvery metal, and they did a really good job for thermometers. So in a bulb thermometer, the liquid in the thermometer expands, or it rises, along with an increase in temperature. Let's see how that works. Why does the liquid rise? Well, let's just say we want to use a bulb thermometer to measure the temperature of the air in the classroom. So the red liquid represents the liquid mercury in this case. The green, I just colored them green so they'll show up on the red. If I colored them red, you're not going to be able to see them really well. But these are the molecules, the individual molecules, or particles, I should say, really, because they're atoms, of mercury. The blue particles, they're moving around the thermometer. Those blue particles, they're zipping around. Those are the air molecules that are surrounding the thermometer. So they're moving around, and you can see the particles moving around. Incredible animation for you there. Every time one of the blue particles smacks into the side of the glass, kinetic energy is transferred from the blue air particle to the glass, which is then transferred to the red liquid. That particle in the liquid, the green, is now going to move a little bit faster because it gained some kinetic energy from the blue particle smacking into it. Now the green particles are going to be moving a little bit faster, have greater kinetic energy. As the particles gain energy, they move faster and they spread apart more from one another. They expand, and the red liquid level rises up the glass tube. So you can see the blue particle smacks into the glass. The green particles are going to move faster, and they're going to make the liquid level move up. The faster the air particles, the blue, are moving, the harder they smack into the side of the thermometer. And the harder they smack, the more kinetic energy they transfer to the thermometer. So here we go. Hitting into there, they're going to make the green particles move faster. The faster the blue particles are moving, the higher the kinetic energy of the blue particles, the air. The higher the average kinetic energy of the blue particles, the higher the temperature reading will be for the air. See the blue particles smacking into the glass thermometer, making the green particles move faster. I'm loving this animation. I hope you are too. Notice that there are not more particles of, well, it says alcohol, but it really should be there are not more of the mercury particles. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not that there's more particles. It's not getting more liquid. It's expanding because of the extra kinetic energy, the extra motion. They're moving faster and spreading out more from one another. See, here you go. See, look, they're going faster and spreading out even more. Look at that amazing animation. This continues until the average speed of the particles stops increasing and the level of the liquid stabilizes. We can now read the temperature. So this is the end of part 2. The next part of this lecture series was going to go over the units of temperature and how to convert the different units of temperature. Hope you enjoy this. We'll catch you next time. See ya.